Okay, so there's a little bit on the global extrema. Hopefully that answers everyone's questions from Wednesday. And then the other note that I posted, we'll quickly talk about, and then we're going to just do a couple of extra examples for curve sketching. So using all this information that we've learned, so, the intercepts of functions, looking at the limits of functions, the asymptotes of functions, where a function is increasing, decreasing, or where it's concave up or concave down, all these things, we're going to use all of those tools that we learned about, and we're going to apply it to look at a function and be able to draw out its graph. Okay, so these are the steps, the strategy for curve sketching. So the first thing is you find the domain of the function. You see if there's any restrictions. So if you have square roots, you have to make sure the stuff in the root is greater or equal to 0. If you have a rational function, the denominator can't be equal to 0. You would get vertical asymptotes in that case. So that's the first thing. See what your actual domain is. The next thing is that you find the intercepts of a function. So in other words, you want to see what x values you get when y is equal to 0, and you want to see what y values you get when x is equal to 0. Okay, that'll be very helpful for drawing. The next step is you find asymptotes. So if you have vertical asymptotes, in which case you kind of figure out from part 1 if you have a rational function, but also be careful for things like tan. Tan has asymptotes, vertical ones, so does ln or logarithmic functions. So there are a couple functions that you have to be careful of. Ln, for example, or log, you can't have any negative values. And x can't be equal to 0 for your log to be defined. So you have an asymptote at 0. X is equal to 0. And also horizontal asymptotes. And remember, horizontal asymptotes are just when you look at the function and you see the long-term behavior. So what happens is x gets really, really big. What happens if x gets really, really small? And by small, I mean negative infinity. So very negative, I suppose. The next step is we see the intervals where a function is increasing and decreasing, and we find the extrema. So by that, what we mean is that you have to find your critical numbers or your critical points. So you look at f prime of x and you solve it for these numbers. You also check if there are places where f prime does not exist. If f prime does not exist at a certain point, but f does, remember that's the other type of critical number you can have. And then these critical numbers are used to split up our domain, which will tell us the different regions where the function will be increasing or decreasing. And then we take a test point within those regions, see if f prime is greater than 0 or less than 0, and then that tells us where the function's going up or where it's going down. And to see what the extrema values are, you can use the first or second derivative test to see if something is a relative max or a relative min, and then whatever one's the biggest would be the global, whatever one's the smallest would be the global minimum. But sometimes, and many times, if you do curve sketching on the whole domain, you don't necessarily have global. It depends on the function. Okay, find the intervals where f is concave up or concave down. This is when you find the points of inflection. Okay, so you have to take the second derivative, set it equal to 0, and then those are points of inflection. Also, similarly, if your f double prime does not exist at a point, but your function does, that's the other type of point of inflection that you can have. Once you have these points of inflection, it again tells you how to split up your domain in order to see where the function is concave up or concave down. And remember, concavity tells you about the shape of a function. Is it sort of like a smiley face or a frowny face? And something else we're going to do today, I think we'll have enough time, is we're going to actually look at some of the COVID data because when you see the change in concavity, it gives you a better idea of if the rate of infection is accelerating, increasing, or decreasing. So if we don't get to it, we'll definitely do it on Wednesday, but I think we'll have enough time to look at some of the things. Yeah, real life math. It's a great example for showing why concavity is so important. And then 6 and 7, technically I should have put them in one. Number 6 is I typically plot all the points of interest first, so the intercepts, if you have any vertical asymptotes, things like that, and then you connect all the points with the information in our first and second derivative charts. And another step for those, you don't have to do this step. It actually wasn't, it's not typically taught in this course, but I put it here anyway because it'll give you a better idea if you're on the right track or not. You can also look at symmetry of the function. And we talked about this, I think, the first or second week of class, that symmetry, so if the function is the same on the right and the left of your origin, we refer to that as even. And a way to test if a function is even, so think of a parabola, for example. You could fold your graph in half and it's the same on both sides. If you plug in negative x into your function, you're going to have squareds or to the power of even numbers. So you're going to get the same thing back, f of x. For odd, if you plug in negative x and you are able to factor out a negative in front of the function, that's an odd function. But a lot of functions don't have symmetry, either even or odd symmetry. So this doesn't always work, but sometimes it does, for polynomials especially. And so then I gave you this example. So it's sketch the following curves using calculus. This is the curve that I've already posted online. So it's a polynomial to the power of 4, so 4th degree, but it only has a quadratic term with it. And for our first step, our domain, there's no restrictions. We don't have roots, we don't have denominators, we're good. So the domain is all of R. Next thing is the intercepts. Okay, so I put f of x is equal to 0, and then I solved, and I got x is 0 and x is plus minus 4. Okay, so there's 3 points where a function is going to cross the x-axis. For the y-axis, the only time that it'll cross is at the origin. So that's our y-intercept. There are no vertical asymptotes because we don't have a rational function. And for a horizontal asymptote, so checking if x goes to infinity or negative infinity, this is a polynomial. So, you put infinity into here, it gets really positively infinitive, okay? Blows up to infinity in the positive direction. Same thing here. So this means that horizontal asymptotes do not exist. That would be if it was approaching a specific value. But it at least tells us that towards positive infinity and negative infinity, we should be going towards the infinite direction in the y-axis. Next thing is the critical points. Okay, so take our derivative, set it to 0. We're going to get 3 critical numbers. And I write out what the full critical points are right away. So if you plug in 0, you get 0, 0 for one critical point. And then if you plug in positive root 8 and negative root 8, these are the ones you're going to get. And notice that even though root 8 and negative root 8, they end up giving you the same y value. And this is actually because of symmetry, which I check at the very end. Anyway, it splits up our domain in the following. Okay, so we're going to have 4 different intervals to check. I put it into a chart. I saw where my function's decreasing and increasing. I stated where that was. And then using the first derivative test, I could state whether these critical numbers are relative mins or maxes. Okay, and we have 2 relative mins at the plus minus root 8, and then a relative max at 0, 0, 0, the origin. Then I check for concavity, so differentiate again. I end up getting 2 points of inflection. Okay, and again, it's going to be symmetric on the plus and minus x side. Once I find those points of inflection, I find the full point, so what the corresponding y values are. Tells me how to split up my domain, and then I can check for concavity in these 3 regions. Okay, so I get concave up, down, up. I state where this is. And then I just do this to kind of remind myself roughly what things should look like. And then I also do a quick little symmetry check. You don't have to do this, but I'll probably do it in the examples that I post. Just for those of you who are familiar with this definition, it may help you out. And then I plotted the graph, and it's going to look something like this. Okay, so that's just a quick rundown of what's been posted. Let's do a curve sketching function. What was the one I wanted to do? I wanted to do this one. So f of x is equal to e to the power of negative x squared. Okay, so we're gonna sketch this graph. Sketch this graph using calculus. And actually, this one's accidentally also very good for COVID stuff. So this is going to work out well. Okay, so step 1, domain. What is the domain of this function? Do we have any restrictions? E to the power of either x or negative x. Remember that graph, depending if it's positive or negative exponent, either looks like this or looks like this. Oh, sorry, it wasn't supposed to go up like that. So e to the power of whatever, plus or minus, it's greater than 0. So we're going to note that e to the power of x squared, this is always greater than 0. It doesn't even equal 0. But the x's itself that you could use, okay, so I guess actually, sorry, that's the range. So the range is going to be positive, but you can take any value of x. But f of x is defined for all x, but the outputs are positive, my apologies, are defined for all x. So the domain is equal to r, but we are also going to write down the range. The range, because it'll help us in this case, is equal to positive r, not including 0. Okay, so that'll help us with our sketching. So there's step 1. So we know information about our domain. We also put extra information about our range. The next step is we want to look at intercepts. Okay, so we want to look at x-intercepts, and then we also want to look at y-intercepts. So this one is when y is equal to 0. So we have f of x is equal to e to the negative x squared. Excuse me. And we want y is equal to 0. Is it possible for this to ever happen? For the e to the negative x squared to be 0? No, it's not. So this is not possible. So the function, so f of x never crosses x-axis. Perfect. So now what we're going to do is the y-intercept. So this is when it corresponds to x as being equal to 0. Okay, so again, we take our function. I'm going to move this up a little. F of x is equal to e to the negative x squared, and we are subbing in 0. Okay, and I'm going to call this y here, because f of x, whenever you actually plug in a value of x, it'll give you a corresponding y. So then we get e to the 0 squared, to the negative 0 squared. So what's e to the 0? E to the 0 is just 1. So y is equal to 1. So our y-intercept would be the point when x is 0 and y is 1. So y-intercept is 0 and 1. Now let's go to step 3. These are asymptotes. So do we have any vertical asymptotes? No, we don't. We don't have a denominator. This is an irrational function. Okay, so no vertical asymptotes. Now let's look at horizontal asymptotes. Now to do these, we're going to look at the limit as x goes to infinity of f of x. So in other words, I'm looking at the limit as x goes to infinity of e to the negative x squared, infinity. So this is going to approach something, okay, so approach e to the negative infinity squared. Okay, so basically e to the negative super tiny number. So what does that approach? And remember, you can think about this like 1 over e to the infinity squared. That may help you see it faster. It goes to 0. But this is the intuition. If you were to plug it in, this is the kind of thing you're thinking of. Okay, so that's good. And now let's do in the other direction. So the limit as x goes to negative infinity of f of x. So the limit as x goes to negative infinity, e to the negative x squared. Okay, so in this case, even though it's negative infinity, the same thing happens. I have e to the power of negative, bracket, negative infinity, bracket squared. So it's equivalent to this expression here. It's like 1 over e to the infinity squared. So it will also go to 0. Okay, so step 4. This is finding our critical points. Okay, so we need to solve, actually we'll phrase it that way, f prime of x is equal to 0. Okay, so remember, I'll put what f of x was here on the side, just so we don't forget. So what is f prime of x? So you rewrite what you have, e to the power of negative x squared, and then we multiply by the derivative of whatever is in the exponent. And that's going to be, the derivative of negative x squared is going to be negative 2x. The negative 2x to the front, and then I have e to the power of negative x squared, and I want to solve this when our f prime is equal to 0. So what does this give me? And I have to be very careful, right? Because this part never is equal to 0. So this part basically, this is never 0, so we can think about it like just dividing it out. It's going to be some positive number, so I'm only left with negative 2x. X is equal to 0. And when x is equal to 0, so this is our critical number. And the point, so if we were to actually plot it on the graph itself, this gives the critical point of 0, and then we have to put 0 into f to see what y value that corresponds to. And if I put a 0 into the top here, that's just 1. So this is 0, 1. This tells us how to split up our interval. So this tells us to split up our interval as, so we're going to get a nice little line here. This is going to negative infinity, the left direction. This is going to infinity. And the only critical point I have is just x is equal to 0, or critical number, excuse me. Okay, so now we're going to make a chart, and we are going to look at intervals going from negative infinity to 0. Okay, so this first little region here. And then the second region is from 0 to infinity. And then our f prime of x, okay, this time we really kind of butchered it. So what was it? It was negative 2x e to the negative x squared. So that's what we're going to be putting our, our test point in. And then we're going to find out if our function is increasing or decreasing. Okay. So somewhere between negative infinity and 0. So, I mean, we could do something like negative 1 if we wanted to. That's not too bad to calculate. So f prime of negative 1. So I'm going to get negative 2 times negative 1. That's a positive. And then e to the power of negative 1. But remember, the e part itself is always positive. So this is going to be a plus times a plus. This is greater than 0. See, I didn't leave myself enough room here. Can I move this over a little? Yeah. So this is greater than 0. So what does that mean about our function? It's increasing. Perfect. Now let's maybe try one. We'll be symmetric. F prime of 1, so I'm going to get negative 2 times 1. And remember that E, that itself is always going to be positive. So we have a positive times negative 2. This is going to be less than 0. So the function is decreasing there. So f of x, make it a tiny bit bigger. There we go. So f of x is increasing on negative infinity to 0, and f of x is decreasing on 0 to infinity. Okay, and I'm going to cheat and copy and paste my number line here for a moment. Make a nice little picture for myself. When you make math more artsy, it's much more pleasant. And the first part of the interval, so from negative infinity to 0, I have that my function's going up. Okay, and then in the second interval from 0 to infinity, I have that my function is going down. So let me move that down a bit. So by the first derivative test, what kind of extrema does that make 0? Relative max. Relative max. So I'll say here, by first derivative test, x equals 0 produces a relative or local, whatever you prefer, max. And we already know what y is at 0. We found I almost said upstairs, up here. Oh, other page actually. Oh, here we go. F of 0 is equal to 1. So it also corresponds to where we're going to have a horizontal tangent. Okay, so these are all little clues on how it'll look. Step 5. So now what we need to do is we need to solve f double prime of x is equal to 0. This will give us our points of inflection. F double prime. So here's our derivative, where our first function, negative 2x, and then the second function is our e. Okay, so by product rule, the derivative of the first, that's just going to be negative 2 times the second, plus the derivative of the second, which we've already actually found. It's that negative 2x e to the negative x squared. Okay, it's actually right here, because e to the negative x squared was our original function. And now don't forget to times this again by the negative 2x, okay, by product rule. So now let's see what we have here. So we're going to have negative 2. And since I actually have an e in both my terms, to make my life a little bit easier, I'm just going to factor out that e right away. So I also have more room to write this stuff down so you can see it more easily. So e to the negative x squared. Now my first term, I have a negative 2 left over. So second term, I have negative 2x times negative 2x. So I'm going to have a plus 4x squared. And I want to solve this when this is equal to 0. And I could actually factor out a 2. Let's do that as well. So I have 1, 2, and then I have a 2 here. This part here, remember, this is always going to be greater than 0, so that doesn't matter. So I have 0 is equal to negative 1 plus 2x squared. Remember, we're trying to solve for x. Let's bring the 1 over to the other side. Okay, so then I'm going to get x squared is equal to a half. So we're going to have 1 over root 2, but the plus minus. Our points of inflection are negative 1 over root 2, and then f of negative 1 over root 2. That'll be the first one. 1 over root 2, f of positive 1 over root 2. Now, what was my f again? My f was e to the negative x squared. So I'm going to be getting e to the negative. It actually doesn't matter if I'm plus or minus because of the squared. Okay, so I'm going to get e to the negative 1/2. Yes. Let's write it like 1 over root e. You don't have to if you don't want to. Oops, sorry, that's positive, negative, this one's positive. And for those of you who talked about even or odd functions in high school, notice that we're seeing the symmetry again. Okay, so if we actually check this, we'll actually do it now, a little note. Note that if we put in f of negative x, we would get e to the power of negative x squared, which would just give us e to the power of negative x squared, which was the same as our function. So our function here is an even function. So the fact that we're seeing these symmetric values, that's a good thing. Okay, points of inflection. Okay, so that's good. So this tells us how to split up our domain to see where the function is concave up or concave down. So this splits up our interval as follows. Okay, we got negative infinity, we got positive infinity, and then I'm going to get this 1 over root 2, and then this negative 1 over root 2. Okay, so now we're going to make our chart. Now, check concavity. All right, so we're going to have 2 intervals. I'm going to zoom in a tiny bit. We're going to have intervals negative infinity to negative 1 over root 2. And then negative 1 over root 2, 1 over root 2, and then 1 over root 2 infinity. Oops. You can already see myself running out of room. I'm going to move this over a tiny bit. Okay, and now, what was our second derivative again? It was f double prime of x is equal to 2e to the negative x squared, 2x squared minus 1. Okay? And then we'll state what the concavity is. Interval. Okay, you know me, I like my zeros. I'm going to use this as an opportunity to do 0. Okay, sorry. So we're going to get basically 2 times 1, okay, because we're going to get e to the power of 0. And then I'm going to get 2 times 0 minus 1. Okay, so this value is going to be negative. So we have that it's concave down. Can we do negative 1? Yeah, 1 over root 2 is a very tiny number. So we can do negative 1. So this would be 2. The e part's always positive, so I'm just not even going to write it. And then we're going to have 2 minus 1. So positive, positive, this is all positive. And actually, we could do a bit of a trick even right now. concave up. So if you want to do the justification as follows, let me flip pages here for a sec. We had up, down, up. So we had happy, happy, sad, happy. Okay, and so these are, this is concave up, this is concave down, this is concave up, this is a point of inflection, this is a point of inflection. So if you wanted to do this and then say, so f of x is concave up in negative infinity to negative 1 over root 2 and 1 over root 2, positive 1 over root 2 infinity. If you didn't do the chart and if you did this little picture, so you should then say here for justification, since f double prime of x is greater than 0 in these intervals. Okay, so that would be your justification. If you don't want to do the chart, please make sure you state this part in green. F of x is concave down in the interval from negative 1 over root 2 to positive 1 over root 2. And then I'll put in green if you don't want to do the chart, since f double prime of x is less than 0 in this interval. Step 6 and 7. Now we're going to sketch. And we're going to do the step 6 first, as in we're going to put down all the special points. Okay, so we're going to do a big chart like that, or a big graph like this, and I'm drawing it more in the positive y-axis compared to a lot of negative y, just because, remember, our range is always greater than 0. Okay, so this is x, this is y. Let's go back to the beginning for a minute and let's see. Okay, so we know our range is only positive. We have all of our x. We never cross the x-axis, so I don't have to put any points there. But I do cross the y-axis at 0, 1. No vertical asymptotes and horizontal go to 0. Okay, so let's flip back for a second and put in some of that information. So I'm going to say 1 is actually, let's do it like up here. So say this is equal to 1. So I have a point here. This is going to be the y-intercept. But this was also another special point, right? This was... Oh, not inflection. This was a critical point as well at 0, 1. So we know that we're going to have a horizontal asymptote also at this point. Okay, so I'm going to draw myself here. So this is also the critical point. And I know however I draw my graph, I'm going to have that it's going to level off there. And I know that as x goes to infinity or x goes to negative infinity, my plot should be somewhere down here. It should be approaching 0. So I'm just going to put those marks there for myself to remind myself. So, okay, are these all my important points? Critical point, and then I'm going up. And then I'm going down. And I know that that 0, 1 produces a relative min. So I know that my graph is doing something like this and then something like this. Now, points of inflection, where the second derivative is 0. Where were those again? Those were negative and positive 1 over root 2. And y is 1 over root 3. So it's a small number. It's less than 1. Okay, so somewhere, so this is not exactly to scale, that's okay. But somewhere here, I'm going to say that that's 1 over root 2. And then somewhere here, I'm going to say that this is negative 1 over root 2. And I'm going to say, let's say here is 1 over root e. Actually, maybe that's too small. Let me zoom in here. And then I have 1 over root e. So I have inflection points. Let's do those in what? Pink? So I have an inflection point here. So this is a point of inflection. And I have an inflection point here. This is a point of inflection. So, and what else do I know? Sorry, about my concavity. I'm concave down, and then I'm concave up towards the end. So I'm concave up, and concave down, basically. So my function has to pass through these pink points, has to pass through the y point, and it has to be the relative max. So this is critical point, and this is also the relative max, sorry. What I'm going to do is I'm going to erase this, and I'm going to do my little dotted method here to make sure I try to draw it as nice as possible. So I know that concave down, so I have like a downward shape here. So I'm going to go up to here. I need a horizontal asymptote, and then I'm going to go back down. Okay, and then I need a concave up shape here. Okay, and towards the end, I'm approaching 0. So I'm doing something, and I have to change concavity, so more sad face than happy. And then I'm approaching 0. And same thing here, more like a sad face. And then I'm approaching 0. Okay, so by super accurate, is this crazy accurate? No, a computer can do this much, much better. And this is not to scale at all. So when you're types of plots, it doesn't matter if it's to scale or not, but you need to label everything. So, you know, this is 1 over root 2, negative 1 over root 2, 1 over e, and then you're saying that this is point of inflection, intercept, all these sorts of things. So this gives a rough idea. This is also called, what? Normal distribution. So I'm sure you've seen things, it's like, oh, flattening the curve. So this is what flattening the curve looks like. It's a normal distribution, which is what you also want your marks to be like. So you get a little peak.